Welcome back. We are down to the home stretch of our statistical reviews training. We have covered quite a few interesting topics, at least interesting to me. We are all very convinced of the importance of checking everything, and we're now going to talk about the last set of things that you have to check. And like everything, I've saved the best for last. Things are going to be less cut and dried. And that's the way it goes. So grab some coffee, sit down, put your thinking caps on, and be ready for some brain teasers here. Okay, we are going to talk about my very, very, very least favorite part of report review. We're going to talk about something that I am not sure that I agree with, and that is implied comparisons. The standards are very clear on statistical testing that they are supposed to support any comparison statements, whether expressed directly or implied. I'm going to come back to this because I'm not 100% sure I agree with this, and you'll find that out throughout the class. However, you have to at least give some time to thinking about whether or not a test is required. And then also the other requirement we're going to cover are historical comparisons. Are they appropriate? That's a tricky one. So we're going to talk about the checklist items 5E, F, and statistical checklist 12. Lots to talk about. So what are you looking for? Well, the first question is always kind of obvious. Are there going to be any comparisons in paper? If there aren't, then really we don't have to worry about this. If they just present some results and say, here's what we saw, but we're not comparing these results to anything, you're in a gray area. Then if they do present comparisons, the second question is, do these comparisons require statistical testing? This is not black and white. It is not always appropriate or required for comparisons. If you don't agree with me, go read all of the ASA's reports in the past several years on comparison testing, on the p-value, on p-hacking. There's a lot of issues with statistical testing. Big issue is something called p-hacking, where you run every possible comparison you can on all your data, and then you pick out the ones that are statistically significant. What is wrong with that? Well, what's wrong with that is, as we all know as scientists, the science experiment starts with a hypothesis, and you would like to reject it. You don't start with, I'd like to find a comparison that's different and publish it. Second of all, and what is just as important, as we know as statisticians, that 1 out of 10 tests is going to reject the null hypothesis. That's our type 1 error. So if you're conducting 10 tests and 1 fails, that doesn't necessarily indicate anything. We expected that when we set our significance level at 10%. So we have to be very, very careful that we're not torturing the data, or as I dare to say, lying with statistics. Going back and getting away from my rant though, suppose you have some comparisons and as a reviewer you say, I think statistical testing is required and appropriate. Then I need to ask the following questions. What significance or ranking tests is being used? And is this appropriate for the data that I'm looking at? Second question you have to ask is, what is the significance level? That needs to be stated upfront in the paper. It does not change for any of the other comparisons. And if nothing else, they can always use the Census Bureau standard, which is 10%. And then again, if the test uses sample survey data, what modifications were used to the test statistics to account for the complex survey design? So many rules and the standards. Really nitpicky, but from a reviewer, they're not too bad to enforce. One thing I already said, the significance level. It has to be 10% or lower. Flip side of that, equivalent confidence level has to be 90% or higher. They have to state that in the paper, and if they do testing, they need to report the p-values. Also, and this is great, you don't have to do this for every single test in terms of the significance level. A blanket statement is permissible. You can say, all comparative statements in this report have undergone statistical testing, and unless otherwise noted, all comparisons are statistically significant at the XX% significance level. Now, as a reviewer, if they make this blanket statement, it is within your rights to say, I want to see all the comparisons. Show me the test results. and they have to do that. You don't have to take their word. And this comes into play, again, if you're looking at these results and they seem suspicious, then you just say, I want to see them. I think there's an error somewhere. Sometimes the need for testing is obvious. If the test says this is larger, this is smaller, this is unchanged, and they're talking about estimates, not process measures like response rates, but estimates. If they are discussing the treatment method effects, we split this survey up into 3 different panels. Panel 1 is our control, panels 2 and 3 are our treatment, and now I'm going to compare effects on this particular estimate based on this treatment. You have to test. Implied comparisons. There is no completely consistent definition. I am not a fan of implied comparisons. I'm a fan of direct comparisons. That said, it always applies to rank estimates. I'll show you an example of that in a second, but if you say something is the largest, it needs to be supported by a test. So let's go back to example 11, revisited. The table says the average home price in Suitland, Maryland increased by $2,000 from 2014 to 2015. Now, as you will recall, we already said, drop the graph, you can't say this, because we have overlapping 90% confidence limits. Therefore, these 2 estimates are not statistically different. We have no evidence that it increased or decreased. Now, suppose the text provided the estimates and the standard errors. That would be nice. We can do a double check. We can say, okay, I'm going to compare these 2 estimates from 2014 and 2015. I have estimate 2015. I have estimate 2014. I have standard errors for both. However, since it's a sample survey and I'm assuming that they are overlapping, there has to be a covariance between the 2. I don't have a covariance, but I could estimate it if I wanted to. If I really want to, give this person the benefit of the doubt, I can say the covariance is equal to the correlation times the standard error of 2015 times the standard error of 2014. And I can get really conservative and say there's no overlap. In that case, the correlation is 0, and I'm just going to add the squared standard errors, otherwise add the variance. Or I can say, I'm going to assume it's 100% overlap. In either case, that T statistic, or I guess actually let's call it a Z statistic for our comparisons, does not provide us evidence of any increase. It is less than 1.645. No good. Now, why did I say T versus Z? Well, as statisticians, we know if you have to estimate the estimates and the standard errors, it's a T statistic. If you know the standard error, it's a Z statistic, but if your sample size is bigger than 30, it really doesn't matter. Your T converges to a Z. Just a little stats trivia to show you guys that I'm up for this game and I know what I'm talking about. Anyway, no way around it. You cannot make this statement. So as a reviewer, you're going to dump this. Oh, I forgot to mention, there is some missing important information in the test. They have to tell you what kind of test it is and how they estimate correlation. Anyway, it's got to be dumped. So I'm just being nitpicky here. Okay, let's go on to another example. Here we have a comparison of 3 treatments, actually, it looks like. Table 1 is going to compare unweighted and weighted response rates by treatment panel using data from the 2014 ASM. So I've got the source and the source of the data and the year. All tests are conducted at a 5% significance level. This is magnificent. I've given you my source. I've given you my treatments. I've told you what the statistics are. I am not only that, I'm going to tell you how I did the testing. Unweighted will use your standard Pearson statistic, and I gave you the SAS-PROC. Yay. And the weighted uses the Rouse-Scott adjusted test, which incorporates complex survey design features. Oof, I am so good. And now I have this table. I have response rates for each of the groups. I have weighted, unweighted. I've broken it down by certainty and non-certainty. Certainty, I don't need a weighted. Obviously, the weight for a certainty case is 1, so there's really no difference. I report the test statistic, and I report the p-value. It's as though I wrote this table myself. Okay, let's start with all. Looks to me like, based on these p-values for our chi-square test, which tests to see if if the treatment effect is independent of the response rate. For both the weighted and unweighted, I have p-values that are much less than 5%. I have some pretty strong analysis. The treatment JJ increases the response rate. Then I look at it for the certainty cases to see if I have any evidence. And my significance level is 5%. My p-value is 6%. No evidence of differences due to treatment for certainty units. Now I look at the non-certainty units, and I find very similar results. I have strong evidence that using this treatment JJ increases the response rates. In these small test statistics, these two response rates are clearly larger. So this is kind of exciting. It looks like I have evidence that I can say treatment JJ increased the response rate, and this is likely due to an increase in response rate for the non-certainty units. And that is indeed what I say. And as a reviewer, I'm pretty happy with this analysis. I've covered all the nuts and bolts in terms of how I got the statistics, and I've provided some pretty strong evidence. Okay, let's go back to our widget production table example. And let's go back to this discussion of ranking. In my tag statement that says the Midwest produces the largest number of widgets. And you look at that and you might say, well, looks like that's true to me. 972 is bigger than the others, except that these are estimates. The probability the point estimate is correct is 0. 0, 0, 0, 0. We have to do some kind of testing here because we are now ranking estimates. As you will recall from an earlier lecture, we know that we can't really make any statements about the West at all. It is not significantly different from 0, given our estimates and standard errors. Typically, what the Census Bureau does now is it's going to do all comparisons, implied or not. So it'll compare the Northwest to the Northeast, the Midwest to the Northeast, Northwest to the South, blah, 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 blah. And we'll have this problem because we can't tell a difference between the Northeast and the Midwest. Now, this is a typical procedure, and using this typical procedure at the U.S. Census Bureau, you are within your rights to say you cannot make this statement. You cannot make any statement because you can't tell a difference between the Northeast and the Midwest using the estimates and the standard errors you provided for me. You might also want to say here, well, the way you're doing it seems a little strange to me because you're not adjusting for multiple comparisons, which we are. So there are probably, I have some concerns there as well. But let's not worry about that. Let's do worry about the direct comparisons and the implied comparisons. So the direct comparisons would be Northeast to Midwest, Northeast to South, Northeast to West, and then Midwest to South and Midwest to West. Anyway, back to this one for a second because I think it's stupid. I think the big takeaway from this is really just that you can't make any statements about the Midwest being the largest because you can't tell a difference between the Midwest and the Northeast. And that is a concern. So you're going to have to tell the author they can't make this statement. It has to be removed. And I, by the way, am not going to worry about all these implied comparisons. The only ones that I really particularly care about are the ones for the Midwest. Okay, so that's an obvious need, this ranking business or this treatment comparisons. Sometimes the need is not quite so obvious. I'm going to give you some examples. Examining the trend with seasonally adjusted estimates, comparisons between different estimators on the same data, or comparisons between different variance estimators. Now, if you're going to do that same data, you could conduct an F-test. And usually, however, this is done without testing. Usually, you'll try to do some kind of simulation, and you'll compare relative levels of relative bias or stability, the variance of the variance. You might also evaluate confidence interval coverage. So I would argue that you rarely need to make comparisons between different variance estimates. Others might argue that I am wrong. All right, let's go back. This is an example of a trend estimate. So we have construction expenditures with a seasonally adjusted annual rate. Can we make a comparison here? Well, it is definitely a steadily increasing trend. When you're putting this table in your paper, or when your author is, they should make a statement that values have not been adjusted for price change over time, inflation, deflation, unless, of course, they have. In terms of being a reviewer, you do not have to worry about finding a statistical test to support this claim of a positive increase. Why? Well, to be honest with you, because there's no agreed upon way to compute the variances of seasonally adjusted estimates. And so you can't do that a test that some kind of ZOT test over time. And what's more important is a feature of a time series is that you have correlated values in the series. To do any kind of non-parametric test like a sign test or a Wilcoxon test, each of these point estimates has to be independent, and they are not. So not only do you not have to do a test, a sign test or a Wilcoxon test would be inappropriate. You would be wrong. Let it go. This is a steadily increasing trend for the most part. Okay, how about this one? We computed estimates of total e-commerce sales by geographic division using a Horvitz-Thompson estimator and a separate ratio estimator, adjusting total sales to the 2017 economic census. So we have estimates and we have their stratified jackknife standard errors, all in 100,000s. Now, just before I go on, I would like to mention someone who gives you these stratified jackknife standard errors should tell you how many random groups. That's okay. This is pretty close. Okay. Table 1 presents estimates and their corresponding standard jackknife standard errors. And then they say, regardless of division, the Horvitz-Thompson and the ratio estimates are indistinguishable. Does this need a test? Well, it's a fair statement. I mean, if you look at how close these are on the same graph, quick and dirty comparison, same data, different method, it's a pretty fair statement. Does it need to be supported by a statistical test? It depends. I myself would argue no. To me, these estimates look indistinguishable. I'm assuming that the divisions are independent, so I could do a sign test. And if I did a sign test to see where my null hypothesis would be, the estimates are different, I would reject. I would conclude that they were, fail to conclude that they weren't the same. But I don't think that sign test would improve the strength of the statement. I think the statement is pretty true, and I don't need a test. There's no gray area here for me, although there is a gray box. Okay, then they say, however, the ratio estimation procedure yields consistently lower standard errors. Well, this seems to be a fair statement. Does this need to be supported by a test? Well, maybe, depending on the reviewer. You could do some kind of sign test because the Horvitz-Thompson is always larger, and you could say this is beyond, what I would expect in random chance. It seems to me to be a pretty standard phenomenon. Or you could say, look at this, these standard errors are smaller. And I might come back to this example, just a little foreshadowing. I mean, the sign test is appropriate if the divisions are independent. The null hypothesis here would be, if it's just random chance, then the Horvitz-Thompson estimate should be larger about 50% of the time. 50% of the time, the ratio will be. So if you used a binomial table to find the probability that 10 out of 10 trials, you'd have larger standard error with a Horvitz-Thompson. You'd have a really small p-value, and you could say, based on my sign test, this statement is justified. Okay. So you could demand as a reviewer a sign test if you felt that the statement needed to be supported. Okay. Sometimes, as I just proved in this last example, the reviewer has to decide. For example, suppose in that last example that we had a minute ago, that you had 2 or fewer ratios where the Horvitz-Thompson's standard error was smaller. You could conclude that it yielded smaller standard errors in the ratio estimator. If in 10 tests you had between 3 and 7, the sign test would be inconclusive. So, that doesn't really help you too much. Then I guess as reviewer, you could say, well, I don't see conclusive results, and you can't make this statement. So that's, how convincing is the author's argument? Yeah, you have to be convinced. The second question, and I think this is a more important question, is, okay, they've made a comparison. Sometimes the test is obvious. In some cases, it's not so obvious. So the next question would be, how hard is it to find an appropriate statistical test that satisfies the conditions in your data and satisfies the test assumptions? And I'm going to go on a limb and say, how esoteric is this test? People can find a test for almost anything. If it is a not well-known test that is not really very well understood, including by yourself, does it really add a lot of value to the paper if it's just to prove that some comparisons can be made? And then the other question that you have to ask yourself is, does the analysis apply only to the studied data? If the authors are not trying to make some global statement about the population and they're not trying to extrapolate, do you need a test? Because the test is really not so much just to separate, phenomena from noise, but it's also used if you're trying to extrapolate or make broader statements. If you're really confining your analysis to the data set at hand, is a test necessary? So let's go back to example 7. This is the one where we had, table 2 with the unweighted unit response rates broken down by collection mode for all of these quarters. So, do I need a test? Well, I mentioned before that unit response rates are performance metrics by statistical period, and these measures are not independent. So sign test is a little bit iffy here. Now, if you look at this table, one thing that you're going to notice, slowly but surely, is in each period, a majority of the respondents respond by web consistently. That's just the reality shown in this table. Will adding a statistical test strengthen this claim? I would argue in this case, no. Yes, I can find a test for this. If I am really, really gung-ho on testing every single thing, I can find a test. And I can guarantee you that you will have evidence then that reporting is done at a highest rate by web. But does that make this test claim any stronger that you have a test? You can look at it and say, wow, I've got these performance metrics. I'm just literally measuring each quarter to see where most of the response rate came from, and most it was web. It doesn't add anything, so don't ask for it. Okay, also remember that testing is not always needed. Sometimes it's not appropriate or useful. Sometimes it's negotiable. Anomalous findings need to be noted in the text, but they don't have to be explained. Also, patterns can be useful even if they are not significant. For example, response rates for units that receive a personal caller is 70%, response rates for units that receive a robot caller is 68%. Probably not significantly different. But if you did a bunch of tests and you consistently got that kind of a difference, it's probably worth noting, that you have two different ways of calling people. One of them seems to give you a higher response rate, not by much, but a little bit. Something worth noting. And again, you can, in this case, make a blanket statement, which says, these results, while not statistically different, show a consistent pattern. All right, let's move on to conclusions and recommendations are supported by the methodology used and the data being presented. Almost done. What are you looking for? We are looking to see that the method used to evaluate the findings is appropriate and makes sense. The results support the recommendations. You're checking to make sure there are no misstatements in the text. So this kind of goes back to that statement I made in an earlier lecture about check to make sure that the results in the table match the results in the text. Now you sort of want to check things like if they say something is larger, it actually is, or something is smaller. You want to make sure that the scope of the recommendation is appropriate. And the author should discuss future research items. Very rarely is a paper completely done or research completed. There's always something to look at. How do you know that it makes sense? Well, how can I put this? I guess I'll just be blunt. You're the reviewer. You're the expert. Use your expertise and experience. You have been assigned to review this paper because you know something about the topic or you have some expertise in the field. Use it. If it doesn't make sense to you, ask about it. Propose alternative methods that do make sense to you. Talk to the author. See what you can figure out here. This is not a blind review, but it should make sense to you. And your opinion here matters. It matters a lot. The author or the co-authors have spent a lot of time looking at this, and they may be fully convinced, and they may not need as much verbiage to explain what they see as you do. You are the first smell test that they're going to have besides themselves. So let's go on to an example. So in this paper, we've defined influential units whose weighted value contributes to an increase or decrease in the estimated month-to-month change estimates greater than 0.01. And this excludes units that didn't report in consecutive months. So we've got some equations here. I've got my equations for the two estimates. I've got my equation for month-to-month change. I'm going to say by this definition, if the difference in month-to-month change is absolute difference is greater than 0.02, I have an influential unit. No problem. Let's look at the simulated data. Table 2 presents the change ratios computed by systematically dropping each unit, along with the difference measures used to identify influential values in our study. And influential values are marked by an asterisk. Okay, so basically I have a bunch of data. I'm going to drop each unit and look at the change ratio. If that change ratio increases or decreases by more than 0.02, then I say it's influential in that absolute difference. And that's the way I did it before. First thing I do is I look at their definition and I look at this table and I notice they missed identifying unit 4. So there's an error right there. They said if an absolute difference bigger than 0.2 means it's influential, they missed one. Okay, that's small. Now I'm going to go back and look at this again. I said, okay, table 1 presents the simulated data. Table 2 presents the change ratios computed by systematically dropping each unit. Influential values are marked by an asterisk. So put them all together here. And I've got 2 influential values, and I have very big change in unit 1, but a very small value. And I have unit 10, which is much larger than the other values, and the drop seems pretty large. So my measure was using this absolute difference in the change metric. I'm a little concerned here. So am I actually convinced that this method is identifying the correct influential values? Maybe I am, maybe I'm not. I look at this point over here for measure 7, and for unit 7, and I drop it out. And to me, even though it's got a bigger change than I'd expect, it doesn't seem to be that influential, at least compared to unit 1. I might want to just discuss this change metric with the authors. I'm not convinced that they're actually appropriately identifying these influential units. Now, that's great. I don't feel these results are consistent with the data. I can veto the paper. I can say major changes needed. I, as a reviewer, probably would. I would say we really need to discuss this metric. Let's go back to example 16. So we made a statement before about comparing the Horvitz-Thompson and the ratio estimator, and we're saying it yields consistently lower standard errors. And we said, well, that seems like a fair statement. Does this need to be supported by a statistical test? And I showed you how you could use the sign test to check this. Just stop right there. Honestly, I wasted your time with that example. I mean, I didn't really, if you don't remember what a sign test is, but I really and truly wasted your time Because if you were to go back and look at your textbook or remember everything that you remember about sample surveys and sample survey estimation, you would remind yourself that the ratio estimates are biased. That bias could be negligible, but it's biased. The Horvitz-Thompson estimator is an unbiased estimator. You use a ratio estimator to reduce the variance. It is a biased estimator. The appropriate comparison is the mean squared error, not the standard errors. In fact, the only thing that you're checking here is that your ratio estimate is actually reducing the standard errors. So it's working as advertised. That's not a finding. So even though the conclusion follows the results, the analysis is not okay. They have to go back and fix this test. There's no reason for a statistical test here, and there's no reason to make this statement. It would only be okay if they said, as expected by design, the ratio estimator is decreasing the standard errors. However, whether it's making the estimates more accurate or not remains to be seen, because one would need to compare the mean squared errors. All right, let's go back to example 2 as a reminder. Way back when we were talking in lesson 2 about this example where we had a comparison that used 21 industries, excluding construction. They were not meant to be represented in the entire economic census. And we said a limitation of this analysis was it was a non-probability sample. The limitation of this slide, and I think in lesson 2, lecture 2, was that it's not 21 sectors that they're only 8. But that's beside the point. Let's go back to the point. It's a non-probability sample. Okay, so they went through and looked at this particular data, and they put out some estimates comparing 2 different imputation methods, producing relative biases, and they are saying anything bigger than 1.02 or less than 0.98 is considered highly biased. And then they make some statements of comparison. Okay, and then they finish off by saying one is better than the other. Okay, first of all, a relative bias greater than 1.02 or 0.98 is considered highly biased. Who considers it highly biased? Where did this come from? We considered, okay. You cite a reference is always considered in the literature. Here are some common references. Okay, otherwise, come on here. I consider a relative bias greater than 0.05 to be highly biased or less than 0.95. Number 2, statement may be true in 15 or 21 industries, the hot deck are less biased than for product 1. But according to our definitions, both sets of estimates are unbiased. Because I said if it's less than 0.02, 1.02 or greater. Anyway, by my own definition, I've got these are less, but I've said they're both unbiased. So is this really a difference to begin with? Also, in a couple of cases where we have the hot deck bias being, in this case, the differences are really large. Should they be discounted in this analysis? I have some big differences here between the 2 methods and not in the same direction. So I'm making a really strong statement about hot deck imputed estimates being less biased, but I have this one case right here where it's much more biased, and I don't even notice that. And I have this other case here where it's much smaller, and I haven't mentioned either of those. All right, now let's go on to 12 or 21 estimates. But now we can go back and we can do a sign test, and I will guarantee you that this is no different from random chance. You would need at least 15 successes to claim that there's a difference. So we don't really have anything that we can say about the hot deck imputed values being less biased for product 2. I can't say anything is clearly better than the hot deck is clearly better than ratio imputation. There's a bunch of cases where the corresponding estimates are really close. Is one method really better, or are they tied? There are a few cases, as I pointed out, where the hot deck imputed estimates are much more biased than their ratio imputed counterparts. And even if I'm using their criteria, There's no justification whatsoever for the author claiming better results with hot deck for product 2. It's very problematic. They can't make this statement. And most important, what? This is a non-probability sample. We've already said that these results are not representative of the economic census of the study. What on earth are we doing letting them get away with even thinking about making a statement that extrapolates beyond these 21 industries? Stop. They can't do it. We need to stop that. They need to make that clear. They need to provide a citation or a reason for their definition of highly biased, or drop the sentence. And they need to make it clear that there's no strong statistical evidence for either method with product 2. And that can and should lead to other revisions. And yes, you may have to cycle through. And with that, we are officially done, at least with this lecture. And now you can go ahead and complete the final exercise. So reread at a minimum section 3 and read section 4 of the paper and complete the remainder of the statistical review form.